Hey guys, what's up? My name is Gabe and this is Games with Gabe. In today's tutorial, what we're going to be doing is a little bit different. This is going to be purely theoretical. There's going to be no coding in this tutorial. And what I'm going to be doing is explaining how triangle collision detection works. We're going to have to do a couple of things because there are a couple things that we have to worry about when it comes to detecting collisions. First of all, the box can be rotated. So we need to figure out how to rotate points about an origin, because that is one of the key factors in determining whether these two objects are colliding, because we have to rotate the triangle to be aligned with the box's axis. So that's the first thing. Second thing we have to learn about is this thing called Bresenham's line algorithm. This is an algorithm that's used typically to clip 3D objects inside of window spaces. So it's supposed to clip a 3D object within one rectangle. And the reason this is helpful for us is because we can use it to determine whether a triangle is intersecting with a square. So that's what we will be using it for. We will not be resolving these collisions, we will just be detecting them, and Bresenham's line algorithm is a fast, efficient way to be able to do that. So as I was going through the mathematics and stuff and trying to explain this last night, I realized this is going to take too long to do the coding and the theory all in one episode, so I'm going to split it up into two. And that's what this is going to be. Let's see how the theory behind triangle versus box collision detection works. So like I said, the first thing we want to do is learn how to rotate something about an origin, because there are chances that we will have triangles and squares that are rotated and they are not perfectly vertical. And so when that happens, we're going to have to make sure that our collision detection is ultra precise and gets it at the exact angle that it is working. So first step to rotate something 90 degrees about an origin. Let's say that this triangle, the center of the triangle is the origin, and we want to rotate it 90 degrees to the right about that origin. So first we transform the shape. As you can see, we have moved the shape to the center. That's relatively simple. All you do is you take the shape's current position and you subtract that from its current position. So it ends up being at the origin, or the center of the axis. And this is important because right now if we were to try and rotate it, it would rotate along this radius. And so if we rotated it 90 degrees, then it would end up right here. And that's not what we're looking to do. We want to rotate it 90 degrees so that ends up in a state looking like that. So after we do the position minus the position, the next step we do is we rotate all the points 90 degrees. So now that they're down here, we can safely rotate every single point and not have to worry about those points ending up in weird positions. So it'll be rotated 90 degrees this way, and then we add the transform back so that they are all in the original position. And what we end up with is a shape that has been rotated 90 degrees about a certain point. Now this is abstracting away some mathematics and stuff. How in the world do we do this? So that brings me to the next part. So as you can see, what I've done is I've blown up this image that I have on the left over here a little bit on the right, just so that we can see what exactly is happening here. What I've drawn out is an angle rotating. So if we were to rotate this point, so say the point was originally here at x, y, and we wanted to rotate it to this new point, x prime, y prime, we know it's going to go something like this and go in the portion of a circle. So we could call this r, and we know this is also going to be of length r. And why is that? Well, that's because we know that no matter what, if we are to rotate a point, say this is 90 degrees, and we want to rotate it 90 degrees this way, we know the length should stay the same. This length should equal this length. And why is that? That's just because that's the nature of rotations. That is how rotations work. They always rotate about a circle. And so, because a circle, if you really want to get technical, is the definition of a rotation, right? So we have this rotation, and we want these two lengths to stay the same, but we want the point to change. And we want to rotate at beta degrees, okay? So we initially start off with this vector, which is at alpha degrees, and we want to rotate it beta degrees. Well, how do we know what x prime and y prime will be? How can we tell? Well, we can use a few trigonometric principles to determine what that will be. So we know that x equals cosine of alpha, right? And we know that y equals sine of alpha, right? Because if we just do the hypotenuse or Pythagoras theorem, then we know that, SOHCAHTOA, all that stuff, we can get what x and y are from this little triangle right here. Well, this one is going to be a little bit different because the triangle is right here, and it's going to be alpha plus beta is the angle. So we know that x prime equals cosine of alpha plus beta, and we know that y prime equals sine of alpha plus beta. Okay, and there are some interesting things that we can pick up here. So if you look down here, I have Ptolemy's theorem, which these are Ptolemy's identities. If you want to go more into depth, I suggest looking it up and looking at some videos on how it works. It's just a little too in-depth for this tutorial, but basically what they state is if you have cosine alpha plus beta, then you get this equation. If you have sine alpha plus beta, it is equivalent to this equation. Well, we have cosine alpha plus beta, we have sine alpha plus beta. So let's see if we can shorten this up a little bit. So right now we have x prime equals cosine of alpha plus beta. That was a horrible alpha. So, well, what does this say alpha plus beta is? Well, we can say x prime equals cosine of alpha cosine beta minus sine of alpha sine of beta. Well, that's kind of interesting because I just so happen to have some things written up here that we know. Hey, look at that. X is cosine of alpha. So we could say that x prime is just x times cosine of beta. And what do you know? Beta is the angle that we want to rotate at. Minus, and what's sine alpha? Well, hey, look at that. Sine alpha is right there. That's y. So we could say y times sine of beta. So we've just transformed it into all things that we know. We know what x is, we know what beta is, we know what y is, and we know what beta is. That's the angle we want to rotate, and x, y are the original point. Let's see if we can do the same thing for y prime. So y prime is equal to sine of alpha plus beta, which is actually sine of alpha cosine of beta. If we're looking down here, this is where I'm looking for this, plus cosine of alpha sine of beta. Okay, well, hey, sine of alpha. I know where that looks familiar, right? That's just y. So we could say this is y cosine of beta. And then cosine alpha. Well, hey, that looks familiar too. That's just x plus x sine of beta. And we've just now transformed this into terms that we know as well. These are all terms that we do know from the just the given that we have. We have the original point, we have the angle we want to rotate by. So more succinctly, we can say that if we want to rotate an angle, if we want to rotate a point about an angle beta, so beta is our angle and we want to rotate the point x, y that much degrees, then we can say that x prime would be equal to x cosine beta minus y sine beta. I'm just going to copy this. And we would say that y prime would be equal to y cosine beta minus or plus x sine beta. There you have it. That's how you rotate points using mathematics. So in programming, what you would do is, like I said, first step you would do, if we go back up here, you would transform the shape. So you would subtract the position out of the current position, so that's centered at the origin. Then you would rotate all the points 90 degrees using this formula right here, the x and the y. And then you would just add the transform back to every single point, and you have now rotated your shape 90 degrees. That's only the first step though. How in the world do we tell if the shape is intersecting with a square? Well, we could break it up a little bit further and just say, okay, if we want to tell if this triangle is intersecting with this square, all we have to do is see if one of the lines is intersecting with the square, right? And we can see that this line and this line are both intersecting with the square. And that's why Bresenham's line algorithm is so important. Before we start talking about it though, I do want to just go a brief overview of logical operations, things that I'm sure you're familiar with, but just in binary, which might be a little bit different to some of you. So in binary, if you have a number like 0010 and 0001, if you say or together, so this or that, this would just basically be, so okay, 0 represents false, 1 equals true, and it's just like programming. False or true is true, true or false is true, false or false, false or false are both false. And then and, which is very similar. So if we have 2 1s and we and these together, 1 and 1, so true and true is true, false and false is false. Let's change that to a 1. False and true is false, false and false is false. So That's logical operations. Just in case you didn't know that, I wanted to go over that real quickly before we actually go into Bresenham's line algorithm. So for Bresenham's line algorithm, I've drawn a few different scenarios onto the screen that will help illustrate how this works. So the top left, we have a line clipping through the corner of the rectangle. Second one, we have a line completely inside the rectangle. Third one, we have a line clipping into the rectangle but not clipping outside of it. Fourth one, we have a line that's almost about, it's clipping through a couple different regions around the rectangle, but it's not actually clipping the rectangle. And then the last one, we have a line that's just completely outside of the triangle. So what Bresenham came up with was this ingenious way of saying, hey, let's just assign all these regions, binary codes. And then what we can essentially do is figure out by ANDing and ORing these binary regions if a line is inside or outside. So this is the basic premise of how it works, right? We assign the inside 0, outside 2. This one is 4, this one is 8, and this one is 16. So you can use 1 byte of memory to assign a region code to every single one of these things. And it just looks like this in binary: 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0. Then next what you do is you could also in your code assign like top, this is right, which is what I did. This is bottom, and this is left. Then what you do is, well, you assign each point by ORing it together with all of the different regions it's in. So this one is in the top region, so P1, or actually no, I'm sorry, I did left to right, so P1 is always the left point. So P1 is 0, 0, 0, 1 because it's only in the left region. P2 is 1, 0, 0, 0 because it's only in the top region. Right here, we get 0, 0, 0 for both of them because they're both inside. Right here, we would get 0, 1 for the left, and then we would get all zeros for the inside. Right here, we would get 0, 1, and it's exactly the same as this one. This one is a little bit different, so we would get, for P1, it's all left, and I actually had a mistake here. For P2, it is the left and the top, and so what you would do in that case is you would OR these values together, so that's 1 or 8, which would give you 1, 0, 0, 1. So that would be your left code. Then what you can do is you can say, okay, if P1 and P2, logical AND, does not equal 0, you have something like this where it is completely outside. And that will work every single time. Why does that work? Well, notice that if you're going to be on this side, you will have a 1 in the right-hand column no matter which region you are in. If both points are on this side, you will have a 1 in this column no matter which region you're in, and so on and so forth for every single region. And so this is really ingenious because then if you AND these together, you know you're going to have at least a 1 in one column, which means that both points lie completely outside the rectangle, and that means that they are not going to intersect with the rectangle. So that's the first part of Bresenham's line algorithm. It's very useful for telling whether a line is completely outside. And the second interesting thing is if a point is completely inside, you will get 0, right? Because both points will be 0, so if you AND them, if both points are 0, then you know it's completely inside. I'm sorry, it's not that you get 0 if you AND them together. If both points are inside, you will get 0. Then the last thing, if you AND them together and you get 0, so this and this, then you know that one point could possibly be inside the rectangle. But as you can see, this is 0, this one and this one are 0, yet this line is not intersecting with the rectangle. And so that brings me to the final phase of Bresenham's line algorithm, which is clipping. So we already know the outcome of this one and this one. I've graded them out because we know this one's completely inside. This is definitely intersecting. We know this one's completely outside. This is definitely not intersecting, and we can tell the case for that every single time. The rest of them are problems. So the next phase of Bresenham's line algorithm is to clip the lines. And so you basically clip the line, you clip that part off, you clip that part off, calculate the region codes again. So then you would get 0, 0, 0, 0 for this and 0, 0, 0, 0 for this, which means that this is inside, this is intersecting. So this is definitely intersecting. We know that now. What about right here? Well, we would get 0, 0, 0, 0 here and 0, 0, 0, 0 here. So this is also definitely intersecting. What about this one? Well, we would get right here, this is going to end up being this top left region code, and this one will also be the top left region code. So I didn't actually change these p-values, but what it would look like now is this would be 1001 and this one would be 1001. And so if we AND these together, since they're both in that top left region, then we would end up getting something greater than 0. So we know this one is definitely not intersecting. This is Bresenham's line algorithm in a nutshell. And as you can see, if you try any orientation of a line in these areas and you do the steps in the order that I specified, you will always get the same thing. You will know for sure whether it's intersecting, know for sure whether it is not intersecting. So just to sort of clarify the steps a little more succinctly, step 1, you calculate the region code for each point. So you come up with your P1, your P2. Step 2, you AND those together. So P1 and P2. Then we have a few different things. So if, we'll say this is equal to our result, if P1 equals P2 and P1 equals 0, it's inside return true. This is definitely intersecting, so we can say intersecting. Otherwise, if res is greater than 0, it's definitely not intersecting. Return false, not intersecting. Otherwise, clip, then repeat from step 1. So we would go back up to step 1 and repeat. So then we would calculate the region codes again after we clipped, and we would do all these steps one more time until we can get a definitive answer, A or B. That's Bresenham's line algorithm. How do you clip though? That's the next sort of hard part if you're in code. How would you clip this? Well, we know this point, we know this point, which means we know the slope of the line, right? Slope is y2 minus y1 over x2 minus x1. So that'll give us the slope. Then what you can do is you can say, oh, well, I know that this point is going to be the left side of the square's x. And then we know that the new y point would be y equals mx plus b. So y equals m times the left side of the square plus whatever the intersection with 0 is, which you could also solve using this equation right here. So you could get a little bit more expanded version, or you could just transform this equation a little bit to give you this in a little bit more succinct form. And so basically that's how you would end up clipping it, and you would do that for both points, and you would do that for every single point. One last thing that I do want to go over real quick before I end this video is how this whole process works. How do you combine the two, the rotating of the points and the triangle collision detection? Well, in our game, we might have a scenario like this, where we have the player jumping and we have a triangle. We can clearly see that these are not intersecting, but with the broad phase collision detection, it's going to trigger, because right there we will have a circle and we will have a circle, and those circles will be colliding. So how do you now tell that there is actually no collision occurring? And that's, we go through a combination of the two factors. So first thing we would want to do is transform the triangle so that it is along the player axes. And so what you would do is you would rotate the triangle negative whatever the player's current rotation is. So the player has a rotation, ROT, and we would rotate the triangle so that's negative that. What that would end up with is you would have something looking like, and you would rotate that about the origin of the player. The player's origin is where you're rotating. Then you would end up with something like this. And then what you can do is you can now proceed to do Bresenham's line algorithm completely the same as you would have if you were doing it on just a normal coordinate axis, because now these are on the same axis. And this will work because, say the player's like this, and the triangle is like this. If you rotate this, no matter how much you rotate it, that point is going to stay within this square, because you're rotating it about this origin, which means that that will always be the same distance, which means it will maintain its space inside the square. So, but it will also make sure that we can do Bresenham's line algorithm and have them on the same coordinate planes. So you would rotate it like this, then you would run Bresenham's line algorithm, and then you would be good. That concludes this tutorial. I hope you guys liked it. If you did, please hit like and subscribe. And in the next tutorial, we're going to actually implement all of this in code. So we will see how this all works when we actually have it implemented. And now you can hopefully see why we have a broad phase and a narrow phase, because if we just did this every frame, this is a lot of work. But if we do the broad phase, which is like literally 2 additions, and then if that fails, we only do this, then we're cutting a lot cutting out a lot of the middleman and just doing this work when we really need to. And then this will ensure that we get completely accurate collision detection, which we will see in the next tutorial. So I'll see you guys then. Hope you like this. See you.